Okay, let's get started. So actually, the topics that we have discussed so far are kind of the basics of the diffusion models. So if your goal is to basically make your own diffusion model, and also if you want to apply those like some kind of the train the diffusion models for some applications, the things that we have discussed so far would be kind of sufficient for many applications. And now what we are going to do is that we are going to go deeper into the theory of the diffusion models. And I think that this is actually kind of the key part, key concept in the diffusion models in terms of like basically having some kind of the different angle in terms of like understanding diffusion models. So as I mentioned at the very beginning of this class, we are going to basically see the diffusion models from the very different angles all the time of this class. And this is kind of the time that we are switching our the gear into that, we are basically now seeing the understanding diffusion models in the continuous time domain. So for the today's topic, probably I guess the today's lecture would be short. There's not much things that I can tell you, but I'm gonna show some kind of lots of the formulations here. But the point would not be basically just like understanding like the formulations, the line by line. I'm going to introduce some kind of some high level the ideas in terms of how we can basically view the diffusion models in the continuous time domain. And based on that, basically what we can do. So previously, basically what we have seen in this class is that we have seen this kind of like some basic formulations for the DDPM, right? So once we basically define the fold, the transition distribution in this way into the Gaussian form, then based on that, this is like the fold distribution that I call as the jump distribution, jumping the xt from the x0. This also could be defined as some kind of another the Gaussian distribution. The another form of the diffusion model that we very briefly have seen in the previous slide, which I call that as kind of the NCSN, but also it's called the other name, the SMLD. This is another kind of the different way that we are defining the fold, the transition distribution into this way, which corresponding the fold, the jump distribution is kind of defined in the other way like this, right? So this was basically the another way of basically defining this kind of the fold process of the diffusion models. Right? So based on that, basically we could see basically how we can perform the reverse process, which is also like performed, like the iterative way. And as I also discussed in the previous the lecture, the downside of the diffusion model is that it's basically taking too much time because of the iteration. So that was kind of the motivation that we started to discuss the idea of the DDIM, which is basically turning the stochastic degeneration process of the DDPM into the deterministic process. In terms of that, we can now reduce the number of the denoising steps up to the 50. So that's also something that you need to basically test in your the first assignment. And the kind of the good thing of the advantage in terms of understanding diffusion models in the continuous time is that now we're going to also see, not today, but until the week of the next week, we're going to see how the number of the time steps can go down to almost the 10 steps like this. So this is kind of the score, which is called FID. So lower means basically the better, which means that the image quality and the diversity is better when this score is basically the lower. So what we can see is that as we obviously increase the number of time steps for the DDPM, at the very beginning, it's basically nothing, but right? But as we basically goes to the 1000, and now we can start to see some kind of some quality images. For the DDIM, even from the very beginning, these steps, we are basically starting at the kind of the better the position here and getting much better as we basically go to the 1000. But if we use some kind of a different idea, for example, like this one, then what you can see is that even with the like almost like 10 to the 15 the steps, we are achieving very the nice quality of the output images. And this is like all done without basically training some kind of the new diffusion models, but just like changing the generation, the process of the diffusion models. So that was a very interesting point in terms of understanding the diffusion models. So what I briefly mentioned last time is that basically in the continuous time domain, the fold process of diffusion model can be formulated into this type of the stochastic the differential equation. So basically, you can see that this is like one type of the differential equation in terms of that we have the xt function here. Is the first derivative is basically also represented as some kind of some function of the linear function of the term itself. But while we are basically having this term, which is basically kind of like injecting some sort of the stochastic. So you can see that if we basically visualize the process of like how this xt goes over the time, you can see that the point here is basically mapped to the other the point here, basically with some kind of some very jaggy, some perturbing some kind of the trajectory. So this kind of the trajectory of the xt can be represented into the SDE. So that's also the kind of the main idea in terms of seeing the diffusion models in the context time domain. Actually, this can be basically some kind of the function of the xt. It does not need to be this kind of like the linear form, but we're gonna basically start to see some kind of the simpler the form in terms of that we are having the linear function here. And when you see basically this kind of the form, what we are going to call is that this term will be called as kind of the drift, the coefficients. So it's basically like it's sort of like moving the mean of the trajectory. And this is the diffusion, the coefficients. So this is about basically the amount of some kind of the stochasticity that we are injecting over the time. So, and this is kind of the Fourier process. And without having any kind of a proof, one of the key things when seeing the diffusion models in the context time domain is that once we basically have some kind of the SDE, the stochastic differential equation, basically defining the Fourier process of diffusion models in this way, then we can directly find the SDE for the reverse process, which is now defined in this way. So you can see that the formulation is kind of very similar with the Fourier case, right? And this is also like a quite interesting point in terms of that once we basically define the Fourier SDE in this way, then we can directly basically find the SDE for the reverse process, which is now defined in this way, using the same the diffusion, the coefficients here, and also the drift term here. But you can see that we are basically having another the term here, which is basically involving this core function that we keep seeing, right? So this is kind of the point. So what we can typically do is that in the diffusion models, so it's basically exactly the same as basically what we have seen for the DDPM case. So in the also DDPM case, we first define the Fourier process, right? And based on that, once we can assume that the noise can be basically predicted, the score can be predicted using the score prediction the network, the reverse process is also automatically defined, right? So it's basically exactly the same thing in the continuous the case as well. Once we define the Fourier SDE, while basically we assume that the score function is kind of known, or kind of like the predicted, then we can directly perform the SDE, the reverse process with this SDE as well. So this is exactly the same thing. So here the thing is that, so basically how we are going to define these two terms, right? So this is the main question. How we are going to define the drift term and also the diffusion, the coefficient term, and what's the meaning of like these terms? So these three things are basically the main things that we are going to discuss today. So let's first go with the last term here. So basically, this is kind of the term in terms of that we are injecting some kind of a stochastic. So this term is basically typically they called as kind of the Wiener process or the Brownian demotion. So which is basically some kind of the real value, some kind of the function, which has some kind of some following the characteristics. So basically, this is the function which is starting at the zero, right? So every time, basically, when the time is zero, it's starting from the zero. So you basically almost surely means that the probability of like starting from zero is basically the one. So that's kind of some mathematical meaning of the almost surely. And then what the meaning of the Brownian demotion is that the increment of each of the time step also follows some kind of the normal distribution. So that's the second characteristics. And the third characteristic is that it's basically independent, which means that every increment from the previous step and also the next steps are basically independent of each other. So this is the third characteristics. And the last one is that also is the continuously function, almost surely, which means that the continuity is basically the probability for the continuity is basically the one for the all the time t. So you can think that this the Brownian with the motion is basically the function that has those kind of the four characteristics. You can see that basically this function is already kind of the one single kind of the SDE, basically having some kind of the stochasticity over the time. So here the question in this default SDE formulation is that how much we are going to inject this kind of the some sort of the stochasticity while basically somehow like moving the point of the xt using the drift term here. So that's the meaning of the default the process. So based on that, what I'm going to briefly go over is that for each of the case of the SMLD and also the DDPM, we are going to see what will be kind of the corresponding default SDE. So from this formulation, can you guess what will be some kind of the corresponding the FT term here and also GT term here? Any guess? Once you see the derivation, you're gonna see that actually the derivation is not that kind of difficult here. But before we get into basically how we can basically derive the default SDE, let me briefly just review some kind of background. Everyone knows the Taylor series, right? So Taylor series is basically nothing but we are basically approximate some kind of increment of the functions with the first and the second and the third order kind of derivatives, right? So that's kind of the basic idea of the Taylor series. Based on that, let me ask you like quick question. So based on this Taylor series here, given any kind of function f, when the t plus delta t can be approximated in this way, what will be kind of the first order the approximate for this function when the epsilon is very small? Do you have any answer for this? 1 minus epsilon 1 over 2? Yes. But yeah, try yourself. Let me give you some time to work on this. Did everyone get something like this? I mean, let me know if you find some kind of typos here, but basically, yeah. Using the Taylor series, if we just take some kind of the first order the approximation for this term, then without the root, then we can compare this, right? So these are some kind of some basic things. So yeah, based on those kind of things, what we can see is that from the fourth, the transition the distribution for the SMLD here, which is defined in this way. Now what we do is that like, the same kind of the fold the mark of the chain, just like replacing t and the t minus 1 into the t plus 1 and the t, right? So then we're gonna basically see those kind of the formulations. So basically what we can see is that these are for some kind of the discrete the time steps, right? Given some kind of the time range from the 0 to the capital T, when you have some kind of the discrete, the finite the time steps, then we're going to have those kind of the fold the mark of the chain. The question is that what if we increase the number of the time steps into the infinity, right? So that is basically the case that we are finding some kind of the corresponding the continuous deformulation like this. Then in the case that when you have some kind of the infinite number of the time steps, the continuous deformulation will look like this, right? So this is basically very straightforward. And from this, based on the Taylor the series, the first order the approximation, what we can see is that this can be basically approximated into this form. That looks like that we are resulting into this formulation, right? So this is kind of like the one specific form of the full SDE in terms of that the drift term becomes 0. While basically we are basically adding some kind of the more the stochasticity over the time. So that's the kind of the full SDE for the SMLD. And which is quite somehow aligned with some kind of the definition of the SMLD in terms of that we saw like the meaning of like this was basically some annulled the Langevin dynamics. Basically, the data distribution was defined as some kind of some Gaussian the smoothed version of the distribution. So at the very beginning, so we are basically gradually increasing some kind of the variance of the Gaussian for each of the point. In terms of that, in the reverse process at the very beginning, we can get some kind of the rough idea for the score function everywhere in the space, and especially we run over time. For the reverse process, the score function becomes like more the precise near each of the data points, right? So that was the basic idea for the annual de-Langevin dynamics. So in the fold process, basically the idea was basically increasing the variance for each of the Gaussian without really moving each of the point, right? So basically this fold SDE is kind of really aligned with some kind of the what we have seen for the annual de-Langevin dynamics, right? So this is basically the one specific form over the fold SDE. But then how about the DDPMD case? In the DDPM case, the transition distribution was defined into this way. So in this case, what we kind of corresponding default SDE. So basically what we can see here is that what we can basically need like the guess is that in the SMLD case, XT, the mean of the transition distribution was just exactly XT minus 1 without having any term, right? So from this, basically, we can see that the drift term here would be kind of basically 0. So basically, no drifting here. XT, the mean of like distribution becomes XT minus 1, right? So every time, basically, there's no kind of the drift here. So that's the kind of the idea in terms of that we're having the full SD without the drift term here. But this is kind of different, right? So we can see that over time, we are basically moving each of the point in terms of that this one get closer to the 0, right? So that is also the basic idea for the DDPM, which means that probably the corresponding corresponding default SDE, the drift term would not be 0, right? There would be some kind of the moving force that each of the point to get closer to the 0, while basically adding some kind of stochastic. So in this case, if we also start to see the corresponding default SDE, then what we can see is that this is the corresponding the Markov chain in the discrete time domain. And here, basically, one small thing is that if we define the beta t in the continuous time by multiplying this like the delta t quantity here, then we can also find the continuous formulations like this. Then using the Taylor series that we have seen in the previous slide, then we can basically approximate the function like this. And we know that beta is kind of the smooth function, right? So we define the beta in terms of that is basically not making some big difference basically for the consecutive time, the time domains. So we can also approximate in this way. Then from this, actually, it boils down to this very simple the form of the fold SDE. And you can see that there is some kind of the moving force in terms like, moving to the point to get closer to the origin, while basically having some kind of the stochastic term with some kind of diffusion equivalence. So which basically shows that we can find some kind of the corresponding default SDE for each of the cases. So we define the SMLD and also DDPM with some kind of default the transition distribution and also default the jump distributions. Based on that, we can now derive some kind of the corresponding default the SDE formulation, which means that by solving this formulation, actually we can perform the fold process in the continuous time domain. And more important thing is that given this kind of the fold SDE, now we can also directly define the reverse SDE as well. So which means that the reverse process can also be performed by just solving the SDE deformulation. So that's the kind of the basic idea. One also kind of a small thing is that while basically skipping some kind of proof here, the meaning of like this formulation is that if we basically compute the covariance for each of the xt for the intermediate the data point, actually the covariance of the intermediate the data point can be computed in this way. Basically, the meaning of like this is that if at the starting point for the data point, if the covariance was basically the 1 with the identity, then we can see that the covariance will be basically preserved as some kind of the identity. So that's kind of the meaning of like this formulation. So that's the reason like why we call basically this the fourth SDE as the variance preserving SDE. So we're gonna use this term for the rest of the lecture in terms of this formulation called the VPSD, the variance preserving SDE, because if the initial decovariance was basically the identity, and this will basically keep going for the OD DXT here, because like this will be the cancel out. Yeah. Actually, this should be 0 here. So this is the there's typo. So that's the kind of the case that we are having the variance preserving the SDE. For the other case, the thing is that for this formulation, the covariance is basically growing over time. So this is the case that the variance is basically exploding. So the fold process, the fold SDE of the SMLD is typically also called the VE SDE. So those are some kind of terms that you need to remember for the rest of the lectures. So now we are basically seeing the SMLD and the DDPM in the contents time domain, which fold process is now defined as kind of the VESE and the VPSD. So those were basically the two formulations. And then here, there might be some kind of the questions. So these are some kind of the two specific forms of the fold SDE, right? Then the question might be is that, then what would be some kind of the other cases? Are these the only cases that we can define the diffusion models? Or can we basically have any random, the kind of default as the SDE formulation for the default process? Do you have any kind of the guess? Would there be some kind of only two equations, or would there be some more other cases as well? Basically, this kind of two formulations basically, bring up this kind of question. What are kind of the other possible cases of like defining diffusion models, right? So I mean, obviously, these two are not the only case that we can define the diffusion models. So that's also kind of the key idea that we are going to discuss for today. We are going to see some kind of the general form of the diffusion models, which is now defined in this way. So before we get into the SDE formulation, we are going to now see some kind of the family of the diffusion models. That's basically is typically called the variational diffusion models. And actually, the previous two cases are basically some special cases of like this form. So basically, the family of the variational diffusion models is basically defined in this way. For any cases that when we are defining the default jumping the distribution, default distribution into this Gaussian form with some kind of the alpha function here and also the sigma d function here. If the alpha and the sigma function satisfies some kind of the conditions, then we're gonna call this as kind of the one of the cases of the variational diffusion models. So you can really check out whether basically the definitions of the SMLD and also the DDPM are really basically satisfying those kind of the conditions. Right? So here, the kind of complication is that we are basically also having some kind of the new notations here. The thing is that these are also basically very new things, right? So we are basically following some kind of the very recent papers, as you can see some references here. The problem here is that every paper uses some like different notations. That's the problem. So we are going to use these specific notations. The thing is that when these like the alpha and the sigma functions, so we are first going to define this term, the signal to the noise ratio. So this is about the signal, right? Because it basically defines some kind of the mean of this distribution. The sigma term is basically defines some kind of noise. This is basically the amount of some kind of stochasticity that we are injecting every time when we sample the xt, right? So when you basically define the signal to the noise ratio as kind of like this kind of term, and when this term is monotonically decreasing over time, then these are all the cases that can be basically seen as like one of the cases of the variational diffusion models. So the meaning of like that the SNR is basically decreasing over time is that over time we are basically adding some kind of the more noise, right? Because at the end, basically what we want to see is that we want that basically after like injecting all the noise in the fold process, the output of the sampling should be basically aligned with the standard Gaussian distribution, right? So the purpose of the fold process is to inject the noise into all of the points that we have. In terms of that, finally it is basically aligned with the standard Gaussian distribution. In a way that in the reverse process, we can go in the reverse way, right? We sample from the standard Gaussian distribution and basically denoise over time in terms of getting back to the data point. Which means that as we basically increase the time in the fold process, we need to inject more noise, right? That makes sense. Right? So in a way that we can basically make all the output, final the outputs to be the samples of the standard the Gaussian distribution. So basically, that's the meaning of like basically decreasing the signal to noise over the time. So basically, when you basically define the alpha and the signal the functions in this way, then we can basically have the results. So like basically aligning the final the outputs to be to the standard the Gaussian distribution. So for all the cases, so this might be also kind of the one specific way or define diffusion models. For basically for all those kind of the cases of the variation diffusion models, if we can basically, so yeah, let me just get into that. So before we basically see how we define the fold process SDE from this definition of the fold the distribution, we're gonna first see kind of the opposite here. So let's say like given the fold process SDE here, when you have some kind of the f function and the g function here, then the fold the distribution here, these two terms are basically defined in this way. So this is kind of the by definition. But you can, based on this, what you can see is that we can go in the other way around. Given the fold distribution, which is defined in this way, we can also consider deriving the fold SDE. So basically, we're gonna get into that later. So what basically, based on this, what you can see is that now we are seeing some kind of the connection between the fold SDE and the fold the jump the distribution, right? And what we have seen for the SMLD and the DDPM case in the previous slide was basically seeing the connection between the fold jump distribution, the transit distribution into this SDE, right? So now what we are going to briefly see is that basically how basically these three things are basically aligned each other. So what we have seen in the previous slide is the fold transit distribution and deriving the fold SDE. And now basically this like fold process, the fold SDE, we can also see that the jump distribution is defined in this way, right? And for the DDPM and also SMLD case, we know these two terms, the jump distribution and the transition distribution and also the jump distribution. So let's quickly check that out, whether these are really aligned. So recall the SMLD, the transition distribution was defined in this way. And this like xt conditioned by the xu was defined this way, right? So from this, we derived the fold SDE, right? And from the fold SDE, we can now see how the jump distribution is defined in this way. So which means that these all three things are basically aligned each other, right? So let's quickly see. So you can download those slides from the selected workspace. So these are basically what we have seen for the SMLD case. So this is our default SDE, and also which was derived from this, right? And then based on this, what you can see is that if we compute the alpha and the sigma, alpha and the sigma d functions, then the jump distribution should be defined in this way, right? Makes sense. So let's quickly check this out. So given this the f and the g function, what should be the alpha function here? And also the thing is that this might be confusing, but actually we already have this like the sigma t terms here. This is the same the sigma t function that we are seeing in the definition of the variational diffusion models. So let's also quickly check this out. By the way, these notations can be confusing, but we are having d sigma and the d sigma, right? So what I mean from d sigma is the sigma function defined in the SMLD. So we should basically align with the variance that we are basically having in the annulled Langevin dynamics. The annulled Langevin dynamics, we are basically increasing the we are having some kind of like Gaussian convolve some kind of function, right? So we are basically gradually increasing the variance of the Gaussian in terms of basically having some kind of the some approximation of this core function over the time, right? So this is the variance that we are basically having some kind of in the annual the Langevin dynamics, and this sigma function is coming from the hourly definition of uh, the variational diffusion models that we are using here, right? And basically, the key things that we are seeing here is that while we have seen some kind of the two specific cases of defining diffusion models, now we are seeing some kind of a general form. For any cases that when we define the the distribution into this way, with this single condition, then the SNR basically monotonically decreases over time. With for any alpha and the sigma functions defined in this way, then we can say that this will be like one specific case of the defining the fold process of diffusion models. So that's kind of the one key thing, right? So this sounds like you can now make your own the version of the diffusion models that basically satisfy this. And then the question might be is that then how can you also see the possible kind of options for the fold SDE, right? So if we can derive the fold SDE from this formulation, then basically we can also find some kind of some family of the fold SDE that is basically aligned with the definition of the variation and diffusion models, right? The thing is that now we are first seeing some kind of the opposite first. Given the fourth SDE, how we can derive the alpha and the sigma functions. Given the diff term and also the diffusion coefficient term, how we can define the alpha and the sigma function. And what we are going to see in the next slide, the later slides, is basically given these two functions, how we can define this angle, right? Then now what we can see is that we can see some kind of some class of some fourth SDE formulation that is basically sending all the data points into the standard Gaussian points, right? So the thing is that while we basically had these sigma functions coming from the different sources, like this is coming from the SMLD, this is coming from the definition of the variation diffusion models. What we can see is that actually these two are the same, right? Basically, what we can say is that obviously the alpha t here should be the one in this case, and from the derivation we can see that actually the sigma d function that we define in the SMLD is basically aligned with the sigma function that we are talking about in the variation diffusion models. So that's kind of some sort of the amount of the noise that we are injecting over the time. So it's kind of like straightforward in the SMLD case. So we could see that from the fold transition distribution, we derived these two things. And from the previous the kind of the formulations, from this we can also define the jump distribution. And these two distributions were basically aligned with our definitions for the SMLD. So this is kind of the clear. It might be slightly more complicated for the DDPM case. So in the DDPM case, we have seen that the distribution is defined like this, and the fold distribution is like this, right? Both of them are the Gaussian distribution. So what we are going to briefly see is that given this definition, we also derive the fourth SDE, right? And from the fourth SDE, now we can also derive this, right? And the things that we are deriving from the fourth SDE should be aligned with like this definition, right? So we're gonna briefly check this out. So the thing is that so if we plug in all the things into the hourly formulation, so from default, the transition distribution, we could see the ft and the gt functions are defined like this, right? But if you just put those things into the hourly formulation, then the alpha t function becomes this, which is kind of like different to what we have seen in the previous slide, right? So alpha t, the meaning of the alpha t function, if we go back to the Bayesian diffusion model, was some kind of the coefficients for the x0 here, right? The x0 here, and which should be the same with these. Yeah, should be same with this term. Which means that the alpha t function should be basically should look like the product of the 1 minus beta t something. But now what we are seeing based on the our formulation is that it becomes like something very different, right? Some kind of the exponential term. But actually, it turns out that actually this the alpha t function is defined this way is kind of the good approximation of like this exponential term. So I'm not going to go into any details here, but actually, if you go down to some kind of the approximation, the formulations here, so you can see that for the jump distribution that we have seen in the previous lecture is kind of the aligned in terms of that it's kind of the good approximation actually of like this formulation. So actually, it turns out that the alpha t function, which is the coefficient for the xu in the four-D jump distribution, actually should be this exponential form precisely in the continuous domain, not some kind of the product. So that's kind of thing. But actually, this product is also kind of some kind of good approximation of the exponential function. The other thing also might be is about some kind of the sigma d function, right? The sigma function should be basically like having this form. Here, basically, the one fact that we know is that the squared the sigma function should be the same with like this term. Can you see why? This is coming from the definition or not definition, the derivation of the default the jump distribution of the DDPM. Can you see why this should be the same? No idea. Because this is basically what we have seen as really for the distribution of the DDPM, right? And this is corresponding to the alpha t function, and this is corresponding to the sigma squared, right? So from this relationship between these two terms, we can see that actually this should be the same with the 1 minus the alpha t squared, right? Make sense? This is basically what we have seen in the previous slide. And from this, what you can say is that this should be the same with the 1 minus the alpha t d squared. So this is like the only thing that we need to check on. So I'm also going to skip some kind of details here, but you can also see later some details here in terms of like how we are basically deriving this one. So, I mean, with this kind of like all kind of the details, I'm going to skip some details. But what you can say is that in the VPSDE case, in the DDPM case, the alpha t function and the sigma t functions are basically defined in this way. So which kind of like looks slightly different with some default the jump distribution that we have seen the previous the DDPM lecture. But actually you can see that these are basically quite good approximation of basically what we can derive in this kind of the case. So this is the case that now we are starting from the definition of the full detention the distribution and deriving the full SDE. And based on that, we are now deriving the alpha function and the sigma function in a way that we can derive the the jump distribution, right? Which is kind of the line with the full jump distribution that we have seen in the previous lecture. But here the thing is that this definition of the alpha and the sigma the function should basically satisfy basically our condition, which is that the signal to noise ratio, the SNR, should be basically decreasing over time. The question is that is this really true in this case? Can you see that whether this SNR is decreasing over time for this definition of the alpha and the sigma function? Maybe, yeah, let's take some time. Actually, we define the beta t as some kind of the non-declining function. If you recall your memory about what we have seen in the DDPM lecture, you can see that actually the beta t, we define the beta t as some kind of the non-decreasing function over time. So this might be actually something that you are implementing in the first assignment, I guess. But basically, given that the beta t is defined as kind of the non-decreasing function and also greater 0 word greater than the 0 over time, can you see that the SNR becomes kind of non-decreasing function? Makes sense? So basically, this term is non-decreasing and also like all the positive, which means that the integral of like this function would be also increasing function, right? Makes sense? This whole part should be increasing function, which means that when you take the exponential of the minus like this increasing function, this should be some decreasing function, right? Makes sense? And since now sigma is basically 1 minus the alpha t, then this should be increasing function, right? So yeah, decreasing function over the increasing function becomes another decreasing function. Right? Makes sense? So sorry? I think we don't need the decreasing function part. Yeah, it should be this one. It should be all basically the positive some kind of the values. Make sense? So yeah, while we basically define the DDPM without any knowledge about basically any kind of things about the variational diffusion models and also the concept of the signal to noise ratio, naturally our the definition of the DDPM is basically satisfying this condition. The signal SNR is basically decreasing over time. So we can see that DDPM becomes like one of the some special case of the variational diffusion models. So yeah, that's the thing. So what we have seen in the previous slide is that given the fold SDE, we could derive the fold distribution like this. Actually, we want to do the opposite, right? Given any kind of the our definition of the fold distribution, what would be corresponding the fold process the SDE? So this is the main quiz. So if there is no typo here, then everyone should get this answer, right? Did everyone get this? Same thing? Yeah. If you didn't get this answer, check this out later and see how you can also derive this. Yeah, so that's kind of thing. So kind of the summary here is that, while we basically have seen lots of some kind of formulations, what I wanted to deliver for today is that how we can basically connect the fold, the transient distribution, and also the fold, the jumping distribution, and how these are also connected to the SDE formulation. How we can go back and forth between these two. So basically, all the fold, the diffusion, the process can be described into the SDE formulation in the continuous time domain. And for the specifically for the SD, SMLD and the DDPM case, based on the fold tension distribution, we could see how we can also derive the fold SD, right? And also, the thing is that the fold SDE could be basically derived from our definition of the fold the distribution and the other way around. So this kind of the conversion can be done in the both ways. And from this definition of the SDE, we also could see we started to see some kind of some general diversion of the diffusion models. For all the cases, like when you define the alpha and the sigma functions in a way that the SNR is decreasing over time, so that will be all the cases that we are defining diffusion models, mapping all the data points into the standard Gaussian distribution. And for those kind of cases, now we can define the fold SDE, which also the most important part here is that given the fold SDE, we can always basically find the reverse DSDE deformulation. We can immediately basically derive the reverse DSDE deformulation from the fold SDE. The meaning of like this is that given the SD formulation, now we can do the sampling the process with some kind of the discretized time step. So actually what you can see in the kind of the other way to basically see the DDPM, the reverse the sampling process basically is to basically seeing that it's kind of the discretization of like this SD deformulation. So basically the meaning of like this is that we can discretize this SDE into this way with some kind of some finite number of the time steps. And the meaning of like this formulation basically becomes that it's exactly the same like what we are doing in the DDPM case. Every time when you basically predict the score, so when you have some kind of noise predictor, we could say that how we can compute the score from the noise predictor, right? And then every time we are basically computing xt minus delta t in the discrete time step, which is basically computed in this way. So one thing that would be quite interesting to see is that how this formulation is exactly aligned with the reverse process of the DDPM. So there can be some kind of some dirty math, but you can try yourself how this process, this computation is exactly aligned with some kind of the reverse process of DDPM that we have seen in the previous the lecture. So these are like all the connect in this way. So even when you basically see the diffusion models in the with the SDED formulation, with some kind of the time domain discretization, basically the solving the SDE can be basically approximated by performing this iteratively with some kind of the Gaussian noise here, and this will basically align with some kind of the reverse process of the DDPM with the hourly definition of the f function and the g function. So this is basically the different angle of like seeing the diffusion models from the perspective of the contents time domain. Make sense? So I strongly recommend trying this yourself. Basically re-implementing DDPM in this way. So with the hourly basically derivation of the f and the g function of the DDPM, we can really just try to compute the reverse process in this way. Then we realize that actually this becomes exactly the same with the reverse process of the DDPM. Makes sense? Kind of the interesting point. Actually, so this was kind of the one thing. The more important thing that we're gonna start to discuss the next time is that without any kind of like the proof here, the thing is that for any kind of some SDE the formulation, which is making this kind of trajectory for the ST. Here the question is that can we find any kind of the ODE formulation, the ordinary differential equation, without the Brownian demotion, without the Wiener process, in terms of that after the mapping from this point to the other points here, the marginal distribution of like those points become the same, right? So basically all the like SDE formulation is all about the mapping, right? So given the samples from the given the data distribution, what we want to do from the fourth process is that all the samples are basically mapped to one of the points of the standard Gaussian distribution. And the reverse process is also the mapping the other way around, right? Through this kind of the SDE formulation and adding some kind of the stochastic. And the question is that would there be some kind of the ODE formulation without the stochastic, which is basically having some kind of the same mapping. So not exactly mapping this to the same point, but basically kind of like mapping the whole distribution here into the same distribution here. That's what you want to do, right? Basically, the purpose of having the SDE formulation is basically to map the data distribution into the latent distribution and the other way around, right? So given the SDE, would it be possible to find some kind of some ODE formulation without like zero the Brownian terms in terms of like having some kind of the same mapping of the like data distribution to the latent distribution? The answer is that, surprisingly, the corresponding the ODE formulation is basically defined in this way, without any proof here. So you can see that actually the formulation is even is quite similar, right? Especially for the reverse process, when the SDE is like defined in this way, with the drift term the F here, and also diffusion coefficients the G term here, you can see that this ODE formulation, just having the 1/2 here, without the Wiener, the process term here, becomes the corresponding the ODE formulation, which is basically the case that now we are basically having those kind of some jaggy some kind of trajectory, but having the much smoother the trajectory without kind of any kind of random noise. But also it's basically not mapping the point to the same point, but the mapping the entire distribution to the same the latent distribution. Then what we kind of the interesting point of the having the ODE formulation. So in the previous slide, given the SDE formulation, we could see basically how we can solve this kind of SDE with some kind of the time domain discretization, right? Basically having some kind of XT over the time. We can do the same thing for the ODE formulation. It's exactly the same type of the Euler discretization that we are also predicting the score every time and also updating the XT through the same formulation, but without the Gaussian noise injected here, right? So this also can be done in the same way in the ODE formulation. The thing is that for the ODE formulation, this is basically subject that has been studied like more than, I guess, like 100 years, right? So there are lots of some kind of the numerical methods that we can solve the ODE formulation in a much faster way without having lots of the time steps. So the good thing of like having the corresponding the ODE formulation is that once we have the reverse SDE and converting this into the corresponding the probability flow the ODE, the PFOD here, now we can use some kind of the ODE solver to perform the reverse process. So that's kind of the key idea in terms of like how we can basically achieve some kind of the much faster speed. So this is the first slide I've shown in today's lecture. Now with DDIM, we are seeing this kind of trend. What you want to do is like having this, right? Even with some kind of very few steps, we already get some kind of the very really good results, right? So we are achieving this kind of a speed up by basically converting the SDE and finding the ODE corresponding to each of the reverse SDE and using some kind of the fast solver for the ODE. And this can be done for the ODE because for the SDE formulation, because of the stochasticity, basically we need some kind of the lots of the time steps to get some kind of the accurate approximation of like this formulation because of like this term. But when we do not have like this term, there are lots of some kind of the techniques that we can solve the formulation much faster. So that's the basic idea in terms of like how we can make some kind of the faster solver for the pre-trained models. Make sense? So in the summary, so each of the diffusion process, the SE has some kind of the corresponding the ODE, which basically matches the same the marginal distribution. So what this means that the reverse process now can be done basically by solving not the SDE, but the corresponding DODE using some kind of any sort of the fast solvers. So this is really important idea. Again, this is also the case that we are achieving all those kind of the things without like retraining diffusion models. For any kind of the pre-trained diffusion models, now we are going to see the same generation process as like solving the SDE, actually even not solving the SDE, actually solving the ODE with the same pre-trained models, just like changing the perspective of the generation process. And basically introducing by introducing some kind of the faster the ODE solver, we're going to achieve some kind of acceleration in the generation process. So that's the basic idea. And we're going to get deeper into that in terms of how we can find some kind of the fast ODE solvers, specifically for this type of the ODE formulation. So before we wrap up today's lecture, we have seen like the four SDE formulations for the SMLD and the DDPM, right? And also for the general case of the four SDE, we also could see how we can also derive the reverse SDE for all the cases, which means that now we can really derive the reverse SDE for each of these two cases. Try to derive the reverse SDE yourself, and especially for the DDPM case, once you derive the reverse SDE formulation with the time domain discretization that I have shown in the previous slide, you can re-implement the reverse process of the DDPM based on the reverse SDE. So I also strongly recommend try this yourself. This is not the part of the assignment. But reason we are providing some kind of some base code for the diffusion model is that you can play those kind of things yourself. So what you are going to see over the second and the third assignment is that from the same base code for the same data set, every time when you change some kind of the generation process, how you can basically get some kind of the almost the same the outputs, but with some much fewer the step of the computation. That would be quite interesting point in terms of understanding the diffusion process, like all the things that we are discussing here. Any questions, Lee? Okay, so as I mentioned, we are not gonna have the lecture this Wednesday, but we are going to